Let us begin with the module on optocouplers or optical couplers. Before beginning with the optical couplers, let us take an example of the telephone line. In telephone line, we can connect say fax machine as well as telephone or any other machine to it. There couplers are required. We call them as either multiplexers or sometimes demultiplexers. Multiplexers actually connect or collect the signal while the demultiplexers distribute the signal. Same functioning is done by the optocouplers. The couplers, that is multiplexers and demultiplexers in telephone line, they are generally electronic couplers. We call them as mux and demux. In case of optocouplers also, such multiplexers and demultiplexers are required. The difference between the electronic couplers and the optical couplers is basically the signal in electrical coupler is electrical, while in optical couplers it is optical. So slightly different configuration and technology is used in order to do that. In this module, we are going to see what are the different configurations which are used in order to couple the signal or split the signals optically. So let us begin with the module on the optical couplers. Learning objectives. In this module, we have to understand about optical couplers, know about different types of optical couplers, understand about the star couplers, T couplers, to understand about the different calculations related to the loss in these couplers, and different optical couplers which are available in the market are also included in this module. As we know, the distribution of optical signal over the more stations is not very simple. For distribution of this optical signal from one network to another or many networks, and to combine these optical signals towards one network is very difficult, and the job is done by the devices called as fiber optic couplers. Coupler is generally defined as a device having one or many input fibers and one or many output fibers. Here we are considering fiber optic couplers. This is because we are considering fiber optic communication link, and if we want to tap certain points, to add certain points or to split certain points, then what we require are fiber optic couplers. Since light is being transmitted through these couplers, it is called as optocouplers. Types of optical couplers. There are three types of optical couplers: directional couplers, distributive couplers, and wavelength dependent couplers. Let us begin with the directional coupler. They generally have 3 or 4 ports, that is inputs and outputs. They are further classified as biconically tapered directional coupler, offset but joint directional coupler, and beam splitting type directional coupler. Biconically tapered directional coupler. Figure shows a fused biconically tapered bidirectional coupler. This is used to provide low loss couplers with a wide range of splitting ratio. Splitting ratio determines how many inputs can be combined or how many outputs in which the input can be splitted. The important parameters which determine the splitting ratio is the tapering length and the cladding thickness. Remember that these couplers are tapered couplers. Now what is the importance of this tapering, that we will see later. It has a very simple fabrication process. In this coupler, 2 multimode or single mode fibers are twisted around one another and put under tension. For softening the optical fibers, and to fuse their cladding, the junction is heated at a proper temperature. A biconical taper at each of the 4 ports is made by pulling on the softened fibers. Consider the case of multimode fibers. If multimode fibers are there in the biconically tapered directional couplers, then coupling takes place as higher order modes, and it is evident that higher order modes are trapped by total internal reflection at the outer surface of the cladding, and then these modes are converted into a cladding modes. But the lower order modes do not travel near the critical angle, and hence they do not be converted, or they are not converted into cladding modes. So, for multimode fibers we can see that the cladding modes or the higher order modes, they are useful for coupling. So, the power of the lower order modes remains in the original fiber. It is observed that the central cladding is common to both the cores, and hence the power from the higher order input modes become common to both the fibers. Thus, the output tapers of the coupler convert the cladding modes back into the core. So, now try to understand the effect of the tapering, and therefore the energy is shared between the two overlapping evanescent waves, and energy is transferred from one fiber to the other, and this is how the energy coupling takes place between the two fibers. This technique is called as evanescent field coupling. Offset butt joint directional coupler. It is a 4-port directional coupler as shown in the figure. Input is provided at port 1, and port 2 collects an amount of power determined by the amount of offset. A fraction of incident light travels from the joint to the tap, that is port 3, along the planar curved waveguide. Beam splitting type directional coupler. A partial reflector called beam splitter can be used as simpler directional coupler for optical system. Figure shows a plate type beam splitter and a cube type beam splitter. Now, plate type beam splitter. In this, partially reflective coating is placed on the transparent substrate. It displaces the transmitted beam laterally with reference to the incident beam. Figure shows how the structure of plate beam splitter looks. Whereas cube type is having two prisms separated by partially reflective coating. It is important to note that a beam splitter cannot be employed by itself for dividing power amount fibers. The presence of splitter in the path of light is equivalent to a gap which provides large losses at the diverging rays emitted by the input fiber. A slight variation of the beam splitting coupler is shown in the figure. The coupler is made by two quarter pinch GRIN rod lenses, that is graded index rod lenses, separated by a partially reflective coating. The fibers connected the coupler are offset from the axis of the lenses. If port 1 is taken as input port of the system of lenses, it will allow the light to go into the second port. The light which is reflected by the coating is imaged onto port 3. No light reaches to port 4. Inputs at the other ports are similarly distributed. Directional coupler using 4 graded index rod collimating lenses attached to the fiber. The problem associated with the splitter is overcome by this type of coupler. In this, the rays are collimated and they are incident on the beam splitter and refocused the divided light onto the receiving fibers. Figure shows such arrangement where GR-ion rods are replaced by convenient spherical lenses. Star couplers. There are two types of star couplers, transmissive type and reflective type. Now let us begin with the transmissive type. Figure shows the basic structure of transmissive type star coupler. In this, optical signals are sent into the mixing block for any single input fiber which is available at all output fibers. The number of input fibers is the same as the output fibers. Power is evenly distributed. Thus, output power P out is equal to input power P in upon N, where P out is the power at the single output fiber. Figure shows the block diagram of transmissive type star coupler. Let us know about the reflective type star coupler. In the reflective type star coupler, figure shows the basic structure of this coupler. The other calculations of these type of coupler is same as the transmissive type star coupler. In this, input power is equally divided into number of output ports. The splitting loss increases logarithmically with the increase in number of output ports. T couplers. Figure shows T coupler. Power is fed into the port 1 and is split into two parts, P2 towards port 2 and P3 towards port 3. P2 and P3 need not be equal. Splitting is determined by the detailed coupler structure. The splitting is expressed either in decibel or in percentage. The most important term associated with T coupler is its directivity. The directivity of T coupler is defined as the power ratio between one port and another port, which is 0 for ideal directivity ratio. As discussed earlier, optical signals are either splitted or combined as per the requirement of the system. For that, fiber optic couplers are used. They are of two types. One is passive and active. In case of passive couplers, the signal is not converted into electrical form, that is, it remains in the optical form. Different optical components like lenses or prisms, waveguides are used in order to combine or split the optical signals. The micro-optic technology along with the integrated optic technology is used for the fabrication of these components. One important thing that is to be remembered is we require very high precision for the manufacturing of these components. On the other hand, if we consider the optical couplers which are active, there the signal is first converted into electrical form and then it is converted into optical form with a proper processing, that is combining or splitting. The couplers use fiber optic sources or detectors in this. The MEMS technology or integrated optic technology is used for the fabrication of these. The precision may not be required in this case. If we consider the optical couplers and compare them with the electrical couplers, then definitely in case of electrical couplers we have electrical signal and the conversion takes place until there is a connection with the component. If we consider the optical couplers, in case of optical couplers we consider the optical fibers and there should be a proper alignment of these optical fibers with the other fibers or with the sources or with the detectors. Then only proper coupling takes place. Otherwise, there will be lot of losses which are occurring. Phototransistor. Since the CTR of a optocoupler with a photodiode output is so low, that is 10 to 15%, a preferred approach is to replace the diode chip with a silicon bipolar phototransistor. The bipolar transistor with its inherent current gain will provide a considerably higher CTR, that is between 50% to 100%, depending upon the beta of the phototransistor. The base lead of the transistor can be reverse biased to reduce sensitivity or forward biased to increase sensitivity or left floating or disconnected. Photo-Darlington output. If a still higher CTR is needed, the bipolar transistor can be replaced with a Darlington transistor. This is required to serve as a photodetector output section. In the circuit, the output current IC of single bipolar phototransistor or the photo-Darlington will develop an output voltage VL across the load resistance RL. This voltage is the product of output current IC and the load resistance RL. The optocoupler can be operated either as a linear amplifier or as a digital switch. It depends on the forward bias voltage that is applied to the base of the transistor. Photo SCR output. If the output section of an optocoupler is a photo SCR, the coupler functions to switch the positive half of AC voltage across the load, operating under the same principle as an ordinary SCR circuit. The SCR gate current is achieved through the photovoltaic action produced by the infrared light impinging on the SCR gate, while optically isolating the input and output circuits of the optocoupler. Steady state DC can be used as the supply voltage, causing the output to be latched on when the SCR is energized. This type of circuit is applicable for security or fire alarm systems. To turn the system off after being triggered on, a single pole single throw normally closed switch for circuit reset can be inserted in the supply voltage path to momentarily remove the supply voltage after the input pulse returns to 0. The momentary opening of the switch turns the SCR off and sets the system to its standby condition. Slotted optocoupler. The slotted optocoupler is available with phototransistor and photo-Darlington photodetectors with the device package structured to provide an additional element of control. The package normally has an air gap between its two sections measuring about 1/8 of an inch in width. One section has an infrared LED and the other a photodetector. Slotted optocouplers with wider air gaps are also available. Applications. The infrared light beam that links the two sections of optocoupler can be broken by mechanical insertion of any thin object into its air gap to block the infrared light. This device lends itself to many control applications. When a thin plastic or metal disc with perforations or slots cut at its outside edge is rotated inside the slot of optocoupler, the infrared light can be detected where an opening in the slot exists. As a result, current flows at the output of the coupler. When the infrared light is blocked by the opaque section of the disc, there is no output current. As the infrared light beam is interrupted, pulses are generated at the output of the coupler and rotational speed of the disc can be measured, and motor speed control can be achieved. If the disc is rotated by the flow of liquid, the rate of flow of liquid can be determined. With a properly calibrated counting system, the exact number of gallons of gasoline being pumped at the gas station can be measured accurately with this device and its associated circuitry. Other applications of slotted optocoupler include a punch card reader, a parts counter, an end of tape sensor, or a printer or tape recorder, and as a part of interlock mechanism. Some specifications which are related to the maximum ratings, such as temperature considerations, that is operating or storage temperature, plastic packages ranging from -55 degrees Celsius to 100 degrees Celsius, hermetically sealed devices ranges from -55 degrees Celsius to +125 degrees Celsius. Then input section ratings, that is about the infrared LED, peak inverse or reverse voltage, that is called as PIV, reverse DC current, continuous DC forward current, peak forward current, DC power dissipation, etc. are some specifications related to the input section. Detector sections. If the detector is photodiode, then the ratings related to reverse voltage, DC power dissipation are given in the data sheet. If the detector section is phototransistor and photodarlington, then the specifications or the ratings related to collector to emitter voltage, collector to base voltage, emitter to base voltage, DC power dissipation are important. If the detector section is photo SCR, then reverse peak voltage, that is repetitive peak reverse voltage, non-repetitive reverse voltage, peak positive anode voltage, peak one cycle surge current, average forward current, peak one cycle surge current, peak gate voltage, peak positive gate current, total power capability are important. If we consider the electrical characteristics of optocouplers, then for the input section, forward voltage, reverse leakage current. For the detector section, if it is a photodiode, then forward voltage, reverse leakage current, turn on time and turn off time. If it is phototransistor and photodarlington, then collector current cutoff, current gain, that is beta or HFE, collector saturation resistance, turn on time and turn off time, frequency cutoff, they are important. If it is photo SCR, then gate turn on voltage, gate turn off voltage, then gate turn on current, forward voltage, reverse current, turn on and turn off times, etc. are important. Let us summarize the module on optocouplers. In this module, we have seen that the star couplers, T couplers, distributive type of couplers, etc., how they work, what is their construction, what are their advantages and disadvantages. If we consider the tapered type of coupler, then what is the advantage of having the tapering? Like in that, we have if we use the multi-mode fibers, then cladding modes are coupled. If we go for the single mode fibers, then evanescent wave coupling is there. So in this module, we have just introduced to you what are the couplers. And finally, we have also told you about what are the different optocoupler types. That is depending upon the detector, whether it is transistor, diode, SCR or Darlington pair, etc. Accordingly, how the output varies. Finally, we have also put some specifications which are there in the data sheet and how it is affecting the performance of that particular device. So, this module will be brief introduction of optocouplers in general.